Hello, everyone, and welcome to our end of term presentation. We'd like to start off with some thank yous because this project would not have been possible without the help from a lot of different people and a lot of different organizations. So first of all, we'd like to thank the 11th Hour Project, funded by the Schmidt Family Foundation, for their generous support of both Eureka and this program. The Schmidt Family Foundation through the 11th Hour Project provides grants to select nonprofit and social impact organizations that work in a few key mission areas, such as human rights, food and agriculture, and energy. And Eureka Recycling, our partner for this project, is one of their grantees. Thank you also to Eureka for allowing us to work with them on this, and to the University of Chicago and the Center for Data and Computing for their support on the academic side. I'd also like to introduce our team. So I'm Liz Nelson. I'm a second year MS-CAP student. We also have Rob Mitchell, another second year MS-CAP student, and Minta Wei, a first year Mac student, and you'll hear from both of them in just a little bit. So I'd like to talk a little bit about Eureka. So Eureka's mission is that they're a nonprofit zero waste organization and social enterprise recycler based in Minneapolis, Minnesota. They've been providing recycling services and zero waste education in the Twin Cities Metro since around 2001. Their facilities process an average of 400 to 450 tons of recycling every day, as well as all the other educational programming they do. And so our goals for this project were to help them understand trends in how often households set out their recycling to be picked up in order to help aid their workforce planning and their route planning, because if there's more recycling on a route, that's more time to pick it all up. We also wanted to help them understand trends in the amount of recycling collected per route. So if there's lots of recycling in terms of tonnage on different routes, the truck might fill up faster, and so they might have to go back again. That also takes time and changes their scheduling. We also wanted to provide anomaly detection capabilities to help flag potential data quality issues to overall improve data collection over time, to inform further operations use cases as they explore the use of data science in their operations. So we hope that our work with Eureka will provide greater visibility into their data collection and quality so that they can explore more data science solutions in the future. So Eureka's data is collected at different stages in its enterprise processes. And so I want to go over that before we dive into the data sets themselves. A truck leaves Eureka's facility and it goes and picks up recycling along a route. And so each of those stops are captured in what's called our fleet mind data set. I'll talk about that more in a second. And then that truck eventually returns to Eureka's facility, and that's collected in a separate data set called PC scale. And that's when the truck is weighed, is when it returns. And so what's actually in these data sets? They're both very rich data sets, but they're hard to unify because they're collected at those two different times in the process and collected by two different separate systems. So the PC scale data set includes information on the date, the route, the truck, the driver, but most importantly, the truck weight. So how much did the truck weigh in tons when it returned from its route picking up recycling? The fleet mind data is collected through the fleet management system Eureka uses, and that has information about each stop along the truck's journey. And particularly, was the recycling out? Were they able to pick it up? Was it out, but potentially they missed it? Or was it not out, not picked up before? We worked to unify these two different data sets, and that necessitated looking at a bunch of different columns in both of these. So we used information from the day of the week, the city, and the route number, as well as the city name. And we linked that with information about which truck was on which route, as well as the date, and then sometimes even information based on the driver in order to be able to match the ending truck weights to those individual routes along that truck's journey. And we were able to match around 86% of Eureka's millions of fleet mind rows this way to their associated truck weighings. And that's actually the first time these two data sets have been linked. And so that really opens up an avenue for a lot of future analyses, both that you'll hear about a little bit more today through our project, but also potentially in future projects with Eureka.
Hi, my name is Rob Mitchell. In this part of the presentation, I'll talk about the problems we ran into on the FleetMind side that we had to solve before merging the FleetMind and PC scale datasets. Solving these problems helped us reach that 86% merged number. The FleetMind dataset has one row for each scheduled pickup of a cart. When a cart is picked up, a row is added to the dataset. If a cart is supposed to be picked up, but the driver missed it, that is also added to the dataset. FleetMind only stores data for about a year before it's archived, and there is a limit to how much data can be downloaded at one time. This meant that in order to analyze Eureka's FleetMind data for all of 2020, we had to download 41 separate files and then combine them, which totaled 6.1 million rows. When downloading the FleetMind data, sometimes the entries would end up in two different data sets. For example, the bar chart shows all the data we downloaded for the month of February 2020. February 10th and 20th were included in two different data sets, so every entry for those dates appeared twice. We had to filter out those duplicates so that we only had one copy of each record. We also had to filter out some rows that we didn't want to analyze, such as canceled pickups. At the end of this process, we had 4.7 million records to analyze. We were then able to merge with the PC scale dataset, and we successfully matched 86% of these rows with entries from PC scale. Finally, we created a version of the FleetMind dataset where we aggregated and pivoted the data so that each row represented the status of all of a route's scheduled pickups on a certain day. By aggregating and pivoting the data, we could look at each route separately and see the status of all its pickups each day that it ran. This allowed us to easily calculate useful metrics, such as the set-out rate of carts or the percentage of carts that the driver missed. Not only did this let us easily create graphs that we could use on the dashboard, it helped us detect when the data was incorrectly collected. For example, if a very high percentage of the pickups on a route were counted as missed, we were able to spot that.
Hi, my name is Mingtao. So with the clean and deduplicated FleetMind dataset, we naturally start to think about what are the core business needs for Eureka and how can we address them using this rich data. We summarize three business cases where Eureka hopes to achieve most easily. They're to understand the time series change in the completion of pickups, people's intent in putting out their cart correctly, fluctuation in the weight of each cart so that they could optimize the pickup order efficiently. However, there does exist some challenge if we proceed to analyze the data directly. Because in that case, the time series trend of fluctuation we detected will be largely distorted by those data collection and processing error. Therefore, conducting anomaly detection before probing into any trend is crucial. This is an example to illustrate this idea. The x-axis is date, and the y-axis is the percentage of completed pickups. We can notice that there's an anomaly falling outside of the 3 standard deviation band. On December 24th, the percentage of completed orders is just 33%. But does that mean on Christmas Eve, very few people are putting out their cart correctly, or too many drivers are just not picking up the recycling? Well, in fact, when we broken down by route, we found that it's actually a data collection error. Many routes were not even running, but FleetMind still recorded them and marked all the orders as missed, which dragged down the overall completed percentage on that day. So when you use these interactive boxes to filter out those weird routes, the percentage of completed orders is back to normal. Now that we have discussed the importance of doing anomaly check, I would like to briefly talk about how we formulate the detection as part of our data solution to Eureka. We rely on 2 criteria to define an anomaly: their percentage of completed orders and percentage of missed orders. We will conduct the anomaly detection on 2 granularities, first on day level and then on route day level. Then we compare these percentages with certain user-defined thresholds. The general workflow looks like this. We're first reading the data from Google Cloud through the pipeline we built, and then we visualize the anomaly detection process in Dash, which is our core product output. Lastly, we will display a table summarizing all the anomalies. This can be downloaded as an Excel file. User could always upload new data to update our existing database. Next, we'll walk through the demo of our dashboard. This is the homepage of our dashboard web application. We can always jump to different pages through the drop-down menu here. So let's take a look at the first page, where we provide a quick overview of Eureka's operation. User can select the date of interest to explore the performance of each route in detail from here. The rest of this page is divided into 2 sections. The first one is a scatter plot, where each circle represents one route on the selected date. And it's worth noting that we have designed interactive input boxes here so that user can have some control over the threshold to determine anomalies. Therefore, all these routes outside the blue region are identified as anomalies on December 31st. The second section is a summary table documenting all the statistics corresponding to each route. We can always click the export button to download it as an Excel file. On page 2, our Dash app displays interactive visualizations of the time series trend for key percentage metrics as well as the count metrics. User can always hover through the data points or zoom in for a closer look. On page 3, our Dash app still focuses on the time series analysis, but we have dived deeper to the route day level. User can use the drop-down list to select the route of interest. We conduct the day level anomaly detection on page 4. By setting the thresholds of percentage of completed orders and missed orders to be 40% and 20% respectively, we managed to capture 12 anomaly days. They can be downloaded to local as well through this export button. Page 5 includes the route day level anomaly detection if users want to flag some weird routes on certain days. The structure is similar to page 4. On page 6, we also display a time trend of the daily weight fluctuation using the data from the PC scale. We can also upload new data through this tab to update existing database. Clicking the navigation bar here will take us back to the home page. All right, I hope you enjoyed our presentation and the demo. Thank you so much for listening.